Right then, in your practical side of your A-level physics course, you are going to have to get used to manipulating equations into the form y equals mx plus c so they can be plotted on a straight line graph. Plotting exponential graphs have their uses, but if you want to find the value of something, you are often looking at the gradient or the y-intercept, in which case you are going to need y equals mx plus c. Some equations are easier than others. For example, the equation for resistivity, Ra over L, you would be changing the length of your wire and measuring the change in your resistance. So you would rearrange this to get your resistance equal to rho over A times L. One trick is to notice that we often plot our independent variable or some form of our independent variable on the x-axis and our dependent variable on the y-axis. So here we have y equals mx plus c. You'll notice there isn't a y-intercept, so your graph should pass straight through the origin. Your gradient is given by rho over a, so a should be a constant for your wire. So by calculating the gradient is rho over a, you can get a value of your resistivity by doing your area of your wire times your gradient. A lot of them won't have a y-intercept, right? Some of them will, and we'll get onto them in a minute. For your free fall experiment, when you're calculating G, you start with this equation. Okay, now we remember that when you're doing your free fall experiment, U is 0 and G is given by, acceleration is given by G. So we end up with this. Now this is slightly different. If I want it in the form y equals mx plus c, if I plot s against t, I would have a quadratic curve. We don't want that. So instead, all we plot is s against t squared. So y against x, where x is t squared, gives my gradient as a half times g. So doubling my gradient would give me my value for the gravitational field strength. Getting into the photoelectric effect, we know that the energy of a photon incident on a metal is equal to the work function plus the maximum kinetic energy of a photoelectron that is emitted. We are changing the frequency of light, and we would then measure the maximum kinetic energy. So our kinetic energy would be on our y-axis, and we would get we would get HF minus the work function, y equals mx plus c. This one does have a y-intercept. What is important to notice if you plotted your graph is that the x-intercept is given by your threshold frequency, below which no photoelectrons are emitted. So we have to extrapolate back to get the work function. It doesn't actually continue. But your gradient is given by Planck's constant. So no manipulation is needed to the gradient. You've already got it in the form where your gradient is equal to your Planck's constant. Getting into simple harmonic motion, the time period of a pendulum is given by this. Now you actually have two options here. You could plot t is equal to 2 pi over root g times root L. So all I've done is split this up, in which case you would get a straight line graph because you're plotting root L as your x-axis, and then your gradient is 2 pi over root g. Or you could take this equation and square everything. So you are now plotting t squared against L. Again, notice there's no y-intercept, in which case your gradient is given by 4 pi squared over g. So your g value is 4 pi squared over your gradient. And you can do something very similar with a mass spring system, where you plot t squared is equal to 4 pi squared over k times m, where your y-axis is t squared, your x-axis is your mass, and your gradient is 4 pi squared over k. So your value of k is therefore 4 pi squared over your gradient. So it's up, there is flexibility in which variables you put on your x-axis and your y-axis, as long as what they are being multiplied by is a constant. You'll notice that that is a constant, that is a constant, that is a constant. As long as they're being multiplied by a constant, you are going to get a straight line graph. And a similar type of equation would be the frequency of the fundamental frequency of a stationary wave on a string. So if I square both sides, I get 1 over 4 L squared mu, because I've split up my fraction, times tension. So my gradient is therefore given by 1 over 4 L squared mu. The tension is given by the weight of the masses hanging off your hanger. So I could plot the masses instead. If you don't want to calculate all the tensions, you could just plot F squared against mass, and then you would get F squared is equal to G over 4 L squared mu times the mass. So your gradient is G over 4 L squared mu, and therefore your mu is G over 4 L squared times your gradient. Just be careful. Y equals mx plus c, m is your gradient, but in this experiment, for example, m is also mass. So just be really careful if you're using mass or you're using gradient. Okay, if you watched my last video on logarithms, you may be able to manipulate this into the form y equals mx plus c. By taking logs of both sides, we can split that log into ln n naught, and then the ln of e to the minus lambda t brings my minus lambda t down, and so I could then plot ln of n is equal to minus lambda t plus ln n naught. So on your graph, you would plot time against number of original nuclei, but the log of the number of original nuclei, with your y-intercept given by ln n naught, and your gradient is minus your decay constant. Because remember, the decay constant is positive, you've got a negative gradient, the gradient is the negative of your decay constant. Last one, which comes with a bonus question, your EMF, if you're investigating internal resistance, is your terminal PD plus your current times internal resistance. Rearranging gives me V is equal to minus Ri plus the EMF, with my gradient given by negative of my internal resistance and my y-intercept being my EMF. Okay. Now, the question here is, why, when my current is 0, does the terminal potential difference equal my EMF? I often ask this question in lessons when teaching internal resistance, and not many students have an answer. So if you have a think about it, let me know in the comments. Why, when current is 0, does V equal EMF? Also let me know in the comments if there's anything else you'd like me to do a video on. I hope that's helped. I'm sure I've missed some. Let me know if I have, and I will see you in the next one. Cheers.